Where's everybody? I guess this is everybody, huh? All right, so we have a lot to do. We only have 4 class meetings, and then we have a final, right? So this week, next week, then finals. So the first thing I'm going to give to you here, we haven't had a quiz in a while. So this is actually the final exam I gave last semester. This is going to count as 2 quiz grades, all right? It's going to be due on the day of the final. So you're going to turn this into me the day of the final, 2 quiz grades. These are the last 2 quizzes we're having right here, all right? So it's pretty much a gimme grade as long as you do it. And, you know, there's one problem on here. Here you go. One for each of you. There's one problem on here that I'm going to have you skip. Yep. Yeah, here we go. There's a few. Please pass those down. Look at that. Thank you, thank you. If you could just pass that down, thank you. Good morning.
Morning.
You ready? Are y'all ready? Test? No? Okay, so again, this is last semester's final exam. It's going to count as two quiz grades. It's due the day of the final, which we'll talk about when the final is. Please scratch out number 3. Scratch out number 3 because, here you go. Scratch out number 3 because that's the telescopic series, which we didn't cover. If you like, you can do it for fun, but you have to come, get some help on it probably. Otherwise, in terms of what you can do right now on this, like starting right now, number 1, you should be able to do. Number 2, you should be able to do. Scratch out number 3. Number 4, you should be able to do it. Number 5, you should be able to do it. Number 6, probably not quite yet. But after today, yes. And then I don't know if we'll get to 7, but we still have, so in your final here, number 7, number 8, number 9, number 10, number 11, number 12, we haven't even talked about this yet, all right? So just give you some idea of how much material is still here for us, all right? Okay, that's everyone clear on that? Due the day of the final. All right, the next thing is, I was asked a few times in class about, finding the sum of a series, right? And how we can only do it for geometric and then telescopic. We didn't cover it, but geometric really is the only thing we can actually find the sum of if it converges. I said it's hard in general to do it. What I thought I'd just real quick show you, remember I told you last time that I do this, in the past I've done this optional lecture on Fourier series. Well, this is actually the lecture that I do. These are the notes for it. And the very first thing gives you a series, and it just says, does this converge or diverge? And then you can very easily do like an alternating series test on that, which we did last class, and you could show that it converges. But then it says, find the sum. Now that we don't know how to do, right? So we can show it converges, but we can't find its sum. Well, the rest of the notes is everything that I have to do to show that that converges, all right? I mean, to find the sum. So look, I'm just going to scroll through it, right? This is all the setup. This is all the work that has to be done. All of this has to be done. All of this has to be done. And then all of this has to be done until you get to your final result. And thus, the series converges to pi over 4. So that just gives you some idea of the amount of work that can be required, right? So that's why we don't do it. We're just not ready for that. And that's only for that series. If it was a different series, it would be different work, okay? All right, so that was it. I just wanted to show that to you. And then we're going to get into the notes today. Let's go. We got a lot of work to do. 8.5, 8.4. So we were talking last time about other convergence tests. And we had done the alternating series test, and then we ended class talking about absolute convergence. And the idea of absolute convergence means that you take a series, and then you take its absolute value and you see if it converges. And if it does, then we say that the original series is absolutely convergent. We also have another definition called conditional convergence. So conditional convergence means that you have a series, it's called conditionally convergent if it itself is convergent but not absolutely convergent. So here's an example. Sum n equals 1 to infinity, negative 1 to the n over n. Here, talk to your classmates about this after class. Okay, so look at this series, right? First of all, let's just look at that series by itself. Does it converge or diverge, right? That's what we want to find first. Does this converge or diverge? Well, does everyone agree it's an alternating series? It's alternating, right? So it's alternating. I'm going to use the alternating series test. The alternating series test says that I want to show two things. First, I want to show that b sub n is decreasing, which is what you're about to say, is decreasing, right? Which means that b sub n is greater than b sub n plus 1, right? And then the second thing you have to show is that the limit as n goes to infinity of b sub n equals 0. Those are the two things on your table, right? Okay, so what is b sub n? Remember, with an alternating series, you have to separate the b sub n from the a sub n. The a sub n is the whole formula in here. The b sub n is only the alternating, no, careful. It's the stuff not alternating. So it's the positive part of the sequence. So if we rewrite this as sum n equals 1 to infinity, we could write the negative 1 to the n here, and then here just 1 over n. Right? So that's your alternating part. The b sub n is this part, right? That's this part right here. So we just need to show that that's decreasing, and we need to show that that the limit goes to 0. Okay? Let's show that it's decreasing. How do we show it's decreasing? Well, we need to show this. Remember this is what we were talking about in class last time? You have to show this is true. So what is b sub n? 1 over n. Is that greater than 1 over n plus 1? All right. And then you do that thing that I don't like to say. N, sorry. Right? And now subtract n on both sides. 1 is greater than 0. Do we agree on that? So it's decreasing, right? Second thing, show that the limit goes to 0. Limit n goes to infinity of 1 over n goes to 0. Check. So what can we conclude? So we did the alternating series test. We showed both conditions were true, right? Both things were true. Therefore, that series converges. So therefore, that converges. Okay? That converges. However, does it converge absolutely? So is it absolutely convergent? Well, we have to take the absolute value of it and then look at that series, right? So now, I'll do it right here. So now, is it absolutely convergent? Question. Well, let's take the series. Let's take the absolute value of this. And when we take the absolute value, the negative 1 to the n doesn't matter anymore, right? Because no matter what this turns into, a 1 or a negative 1, the absolute value is just going to make it a 1, right? So this is just going to be 1 over, and then the absolute value of n, that's just n because n is always positive. So the absolute value of a positive number is just itself. So do you all agree that's the absolute value of that sequence in there? Does that converge or diverge? Please don't tell me that that converges to 0. Because that's what the sequence does. I'm not talking about the sequence, I'm talking about the series. It diverges why? It's harmonic. It's harmonic, right? It's harmonic. So this is harmonic. It diverges. Okay? So therefore, is it absolutely convergent? What's wrong? Yeah.
Where did the 1 to negative n, where did that exponent of n go?
So if I were to do this, right? If I did the absolute value on top and the absolute value on the bottom, right? Do you agree that this, no matter what n is, this is either 1 or negative 1? And if you take the absolute value of 1 or negative 1, you just get 1, right? So that means I don't need to worry about it, right? And then on the bottom, since n is always a positive number, right? This will always just be n. Okay? So this is an example of what we call conditionally convergent. Because what's happening is the original series is convergent, right? The original series is convergent, but it's not absolutely convergent. When you take the absolute value of it, it's not convergent. So this series is conditionally convergent. So it converges, but it's conditionally, I'll just say conditional convergence, all right? All right, so does this make sense to y'all? Look, I mean, if I give you a series, right? If I give you any series and I say, hey, is it absolutely convergent? Then you check the absolute value, see if it converges or not, right? If I ask you, is it conditionally convergent? You have to check here first, right? If it converges here and diverges there, then it is conditionally convergent, right? And that leads us now to the next theorem, which is actually one of your tests on your sheet. It's at the very bottom. I believe it's the very last one on your table. Right here, right. Talk to your classmates about that after class. Okay. So the last thing says, can you all interpret what it says on there? Yeah, it says that if the sum of the absolute value converges, then the original series converges. Now, it's not written the same way there, but on your sheet it says this. I want to keep this up here. It says, this theorem says that if you have some series and you take the absolute value, right? So you're checking for absolute convergence. If this converges, then the original series converges. Which is a great way to check to see if a series converges or not. Just check its absolute value. If that converges, then the original one does. Right? Now you have to be careful because look at this one right here. Did this one converge? No, this one did what? It diverged. Does that mean that the original one diverges? No, the theorem says if this converged, then what could you say about the original one? It converged, right? If this one over here, if the absolute value converges, according to the theorem, the original one must converge. But if the absolute value diverges, you don't know anything. This could converge, it could diverge, you don't know. Right? So you have to be careful the way you read theorems. You can't just assume that the opposite is true. Do I need to clarify this?
Is that just like what we went over yesterday with absolute convergence?
Is that what we...
Because yesterday we said that if the absolute value of something...
Yesterday I wasn't here. No, I know what you mean.
No.
I know what you mean.
We said that if the absolute value converges, then the original series...
Yes, that's exactly what it is. So I did mention at the end of class, right? I just hadn't shown you conditionally convergent yet, so now I'm officially stating that theorem. Okay? So I have an example for this, but I did this in class last time. I did the sine n over, I don't know if I did sine n over n or sine n over n squared. I don't remember, but I did that in class. So look back in your notes. We couldn't tell if that series converged or diverged, so we took its absolute value, and then we showed it converged. And since the absolute value converged, that means the original series converged. So we did that in class. All right, I'm going to move on to the last, hopefully, thing here. Where the hell's my mouse? All right, we have reached the last two tests on our sheet. The last two tests. The next one, I even call it here the almighty ratio test. It's not called the almighty ratio test in the book, all right? I just call it the almighty ratio test because it is a really, really good one. And it's the test we'll be using pretty much the rest of the way in this chapter. And as I've shown you before, even though I'm calling this the almighty ratio test, it isn't the magic pill, right? I told you a long time ago, if there was one test that we could do that works for every series, then that's the only test we would teach you, right? But this one works for what we need later, okay, many times. So what is the almighty ratio test? It's a super nice test, all right? It's actually pretty easy to implement. Here's what it says. I'm going to make this bigger. Okay, so the almighty ratio test. This test is one of the most important and useful tests. It can be used on any type of series, positive, alternating irregularly. So you know on some of our tests we had to have like, you could only use this if you had positive terms. If it was alternating series, it had to be like positive, negative, or negative, positive. We had these conditions. You can use this anytime, all right, which is one of the great things about it. So it says here, all right, we're given a series, right? We're given a series. Now, what we're going to do is we are going to calculate a limit. And what the limit's going to be is something we have not done before. It's the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Remember, this is a subscript n plus 1, not a sub n plus 1, right? So what this is doing is it's taking, if you think about a series, right, a generic series, this is a1 plus a2 plus a3 plus ... And yeah, some of these you might be alternating, who knows, right? But it's just adding up a bunch of things, right? If you go out here to the nth one, right? The one right next to it is the n plus 1. And then it keeps going, doesn't it? Forever. What this ratio test says is you're going to take a ratio of the nth one in the n plus 1 one. So this one in the one before it. And these are arbitrary. So you're going to take this one and divide it by this one. And you're going to figure out that ratio. And you're going to try and determine whether or not that ratio is less than 1, greater than 1, or equal to 1. And we have 3 different possible things that can happen. So whatever this answer is, whatever this limit is, we're going to call it L. We have 3 different outcomes. The first outcome, if L is less than 1, the series does what? Converges. Freaking awesome. Okay, if we get a number less than 1, we have a convergent series. Okay? Now, if the L is greater than 1, it's divergent. Divergent. So this isn't like the pregnancy test, right? Remember that one, intern? It's not like it only is telling you one thing. This one is actually going to tell you if you have convergence or divergence, right? There's one case where this test falls apart, and that is the third case. If that L is equal to 1, the test fails. It can happen, all right? It can happen. But any other scenario we get, we're going to know what happens. And do you remember, we did a thing called the limit comparison test, where we had to take a limit. But remember when we did that limit on the limit comparison test, we were doing a limit of the original series with something we were comparing it to that we had to come up with. And what we needed is for that to give us a positive number. It couldn't be infinity, right? It had to be a positive number. Here, if you get infinity, you're okay, because if this is infinity, infinity is greater than 1. So it works. Also, if you get 0, it's going to converge because 0 is less than 1. So this is a great test, all right? Let's see the test in action. Come on. So we're going to do this first one here. So let's see, we've got sum n equals 1 to infinity, negative 1 to the n times n to the 4th over 4 to the n. All right, we want to know if this converges or diverges. You know what? Am I out of... There aren't any extras? No? Okay. Talk to your classmates about that after. All right. So we could do a lot of things on this, right? We could do, what, alternating series test? You could, because it alternates, right? You could try it. And, I mean, you might take the absolute value of it, right? Take the absolute value, and if you take the absolute value, then you could see if that converged, and hopefully it does. And if it converged, then you would conclude that this one converges, right? But let's use this new test, right? Let's use the new test. I'm going to try the ratio test. Okay, limit. I'm going to take a limit as n goes to infinity. Absolute value. Okay. I need what on top? What goes on top? A sub n plus 1. This one right here. A sub n plus 1. So that means, like we talked about last class, right? This means you're plugging n plus 1 into this thing, right? For all the n's. You're placing all your n's with n plus 1s. Let's do that. It'll be negative 1 to the n plus 1 times n plus 1 to the 4th all over 4 to the n plus 1. Everyone got that? That is a sub n plus 1. Now we need to divide that by what? The original, a sub n. Negative 1 to the n times n to the 4th over 4 to the n. Remember, all of this is an absolute value, right? Now, I know that looks terrible when you first see it, but actually it's not that bad. This equals, I'm writing the limit, right? Because I'm still taking a limit. I'm not going to throw it away. Absolute value. Okay, a couple of things to notice. First, this negative 1 to the n plus 1 is either going to turn out to be a positive or a negative 1, right? And when I take the absolute value, it's not going to matter. Same with this one. This negative 1 to the n, when I take the absolute value, it's not going to matter. So basically, I can throw these two away completely. Just ignore them. Good, right? Now, on this, I'm going to write it down. I have n plus 1 to the 4th, and then on top, that's on top of this, right? Right, that's on top of that. I'm going to write it this way. 4 to the n times 4. Do you all agree that that's what this really means? Yes. 4 to the n times 4 to the 1. So I'm just rewriting that this way, right? Okay, all of that was divided by this, right? But division of a fraction is the same as multiplication of the reciprocal. So I'm going to just take this and flip it up like this. And so I'm multiplying by what on top? 4 to the n over n to the 4. Do you see why I broke this up now? Do you see why I broke this 4 to the n plus 1 up? So it cancels out. Any questions on that step? Okay, cancel this out. Gone, gone. Let's see what we've got left. Equals limit, n goes to infinity, absolute value. Okay, up top, we have n plus 1 to the fourth. And on the bottom, we have 4n to the fourth. Right, that 4 times n to the fourth. Okay, we need to take this limit. Let n go to infinity. Infinity plus 1 is infinity. Infinity to the fourth power is infinity. So you have infinity on top. Infinity to the fourth is infinity times 4 is still infinity. So we have infinity over infinity, right? So, L'Hopital, right? L'Hopital. Let's do L'Hopital. Limit. Oh, L'Hopital, I need to let you know what I'm doing. N goes to infinity. Okay, derivative of the top. I have to do chain rule. 4 times n plus 1 to the third. 4 times n plus 1 to the third times the derivative of what's inside. Derivative of what's inside is 1. So that's it right there. All over, what, 16 n to the third? Still get infinity over infinity? Yeah? Okay, keep going then. Do another L'Hopital. 12 n plus 1, what, squared? Over 48 n squared. This is tedious, huh? We got to keep going. I'm going to show you a faster way when we're done. Limit n goes to infinity. I'm continuing to do L'Hopital because it's getting nicer. Every time I go, the power keeps coming down, right? So this next time, this 2 comes out, hits there, we get, what, 24 n plus 1, just n plus 1, right? And then over on the bottom, we get 96 n. Still infinity over infinity, right? I can go one more. L'Hopital one more time. Limit, n goes to infinity. Okay, ignore the 24. Derivative of that is 1. So 24 on top over 96. 24 over 96. Hey, guess what? That's less than 1. I don't even care what it is. It's less than 1 though, right? What does this mean? It converges. This is a convergent series. Okay, therefore it converges. So let me show you a slightly faster way of doing that, okay? Just slightly faster so we don't have to do L'Hopital like 5 times. Back here at this step right here, where we were right at this step, I can write it this way. So instead of this, I could have written limit, n goes to infinity, absolute value. I could have written it as 1/4 times n plus 1 over n to the fourth. That would have been better because, see, this n is being raised to the fourth, so is the n plus 1, it's being raised to the fourth as well. So I can put those two as a fraction to the fourth. I just need to make sure I peel this 4 out to the front. Y'all with me? Bless you. And then when I take this limit, I can actually push the limit inside that parenthesis, past the power. And I can just figure out what the limit of this is. And what is the limit of that? Well, infinity over infinity, right? And you just do L'Hopital 1 time. And what would you get?
1.
You get 1. And 1 to the fourth is 1, so your answer would be 1/4. Which is, that's what this is, right? Is this 1/4? Wait.
Yeah.
1/4. Okay. Yeah. So just a little faster, but hey, I mean, we did it, right? What do you think? Not bad, huh? Let's do another example. Okay, next one is -1 to the n times n to the n over n factorial. Y'all remember what n factorial means, right? N times n minus 1 times n minus 2 times n minus 3, all the way till you get down to 1. All right. So yeah, I mean, I could maybe try alternating series test. I could take absolute value. I could do a lot of different things, but we've got this new ratio test. Let's go for it. Take the limit. N goes to infinity. Absolute value. Okay, -1 to the n plus 1. Careful here. I'm replacing all the n's with n plus 1s. n plus 1 to the power n plus 1, right? Over n plus 1 factorial. So that's a sub n plus 1, right? That's our original series, or sequence in the series, with n plus 1 plugged in. And now on the bottom, we have a sub n, which is -1 to the n times n to the n, all over n factorial, absolute value, equals limit, n goes to infinity. All right, I'm going to ignore the -1 to the n's again, right? I'm going to ignore that. This right here, -1 to the n plus 1, -1 to the n, I don't care about those. And now I'm going to do what I did before, okay? I'm going to do this thing where I'm going to rewrite this as n plus 1 to the n times n plus 1. Are we all clear on why that's that? N plus 1 to the n plus 1 is n plus 1 to the n times n plus 1 to the 1, right? You put those together, you add the exponents, right? There's really a 1 here, isn't there? Okay, I just don't write it because I don't need it. And what's below that? N plus 1 factorial, right? But is there another way we could write n plus 1 factorial so that we get an n factorial in there? Because remember, we have an n factorial down here, right? Isn't there something we can do with this? We saw something with this before. Can I write that as n plus 1 times n factorial? This is the same as n plus 1 times n factorial. Look in your notes. We did this. I showed it to you back in the day. This turns into this. We all right with that? Now, I'm going to say times. Instead of dividing this by this, I'm going to multiply by the reciprocal, right? Bring this up. So this is going to be what on top? N factorial, and then on the bottom, n to the n, like that. Equals the limit. N goes to infinity. All right, we got some cancellation again, don't we? N factorial, n factorial. Oh, n plus 1s. Hey, how about that? And what are we left with? We have